Today we're going to talk about attention. Oh, I hope these are the updated slides. They haven't changed that much from last year, but if they have, if these are the old slides, then I'll fill in the differences. So I'm going to talk about attention. And attention is basically a really good way to get things done. You read about it in your reading, but basically, in our traditional encoder-decoder architecture, we have the encoder and decoder, and all of the information about the sentence is passed through this one single vector here. And the problem with this is what we talked about in the sentence representation class. So in sentence representations, we have a single vector or multiple vectors. And as Ray Mooney says, multiple vectors are a good idea. And attention is basically a way to not be forced to put all of the information from a sentence into a single vector, but instead be able to use multiple vectors to do translation or whatever downstream. So the basic idea behind attention, which was also covered in the reading, is we encode each word in the sentence in a vector, and during decoding or during sentence generation, we dynamically choose which of the vectors to use to make our next decision. Using attention weights, and we use a combination in picking the next word. So let's say we've generated I hate. We use our query vector here. So this terminology is a little bit different from the reading. This is from a recent paper called Attention is All You Need, which I'll talk about at the end. But I like this terminology, so I'll use it. But basically, we have the query vector. We also have key vectors, and these key vectors are basically what we use to calculate our attention weights. And then for each query key combination, we calculate a score. And these scores can be any real number. And then we take the softmax and normalize, so these become numbers between 0 and 1 that all add up to 1. And then hopefully the weight corresponding to the most important word will be higher than all the others. And then given this, we take value vectors. In the case of something like translation, these are usually the same as the same as the key vectors. And we take these attention weights and we take the weighted sum over these value vectors. And this kind of attention mechanism can be used in any part of the model you like. So people have been very creative in how they use this attention mechanism. Were there any questions about the basics of attention after the reading, or is this pretty clear? Yeah. Okay. So that was review. This is a graphical example that I calculated myself from Japanese and English. The interesting thing about this example is it's could you recommend an expensive restaurant? And basically what it decides to do is it decides to focus on recommend for all of could you recommend. It decides to focus on inexpensive for inexpensive. And then for restaurant, it focuses on restaurant. Then question mark, it also focuses on restaurant for some reason. And then that's how you generate your sentence. Oh, yeah. An aside, sometimes people make black be no attention and white attention. Sometimes people make white no attention and black attention or whatever else. So you can see this both ways. In this case, black is low attention, obviously. So there's a bunch of attention score functions. A couple of them were covered in the reading. There's one new one that wasn't that hadn't made its way into the reading yet. But the original one that people used was the multi-layer perceptron, where basically we feed this through a standard NLP type function, where we take Q and K, we concatenate them together, multiply them by a weight matrix, do a nonlinearity, and then multiply it by another weight vector to get a scalar for each. This is flexible, so it can learn kind of any sort of combination because MLPs can learn any function. It's often very good when you have large data, like enough data to train your model. There's also a bilinear function. So basically what this means is you take k and q, and then you multiply them by, you have a weight matrix in between, and then you take the similarity between them. So this is also a thing you can do. I found this to be less effective than multi-layer perceptron or dot product, but it also kind of depends on what task you're doing and what data you're using. Yeah.
What is the purpose of the W2 transpose? Without that, also you would end up getting some score, right?
So, so the next thing you can do, like, so let me show here. Or what? Sorry, the transpose.
So it's W2 transpose into tan H of something. So why do you need that W2?
Oh, so this tan H can be over a vector of like 512. So this is a standard MLP that's getting a scalar at the end. Yeah. Yes, it's your hidden values. So then the dot product one, this is just the dot product between the two. So the difference between this and the bilinear function is basically whether you have that matrix there. The good thing about the dot product is that this has no parameters. The bad thing about it is it has no parameters, so basically it's easy to train. The problem is that it requires the sizes to be the same between Q and K. Another very recent one that kind of makes a lot of sense, and this wasn't included in the reading, but it seems very attractive to me, is the scaled dot product. So the problem is that basically the scale of the dot product increases as the dimensions get larger. So why is this a problem? So attention is basically taking the softmax. And if we remember what the softmax looks like, it's basically, I'll call it A. It basically looks like this, right? We're exponentiating E to the attention score, right? So let's say we have a dot product over a vector of size 256. And because it's over a vector of size 256, maybe the variance of this is something like, let's say it's 50, just kind of arbitrarily. We have, or no, I'll say it's 5, kind of arbitrarily. And then we have something that's 512, and because we have more hidden units, now the variance of this becomes larger. So we have, I hope I got that right. Variance, or is it squared? Somebody help me with this. The variance of independent variables as you add more increases linearly or squared? Squared. Squared. Okay, yeah, there we go. So now this should be 20, right? So based on this, does anybody see a problem here? So let's say with our 256 one, we get some attention weights that look like 0.2, 0.1, 0.7. So this is kind of a relatively smooth attention function, where we focus on the third word, a little bit more this word, a little bit less than the first word, kind of in the middle. So what happens if we increase the variance of these scores here, or make their scale larger? Any ideas? More ambiguity. That's a good answer, but it's actually kind of the opposite in a way. So what happens is basically you put a lot more weight on the higher answers. So you would get like 0.9 and 0.07 and 0.03. So if you have a bigger scale of your scores, if the scale of your scores gets bigger, then your distribution gets peakier. And if your distribution in attention gets peakier, basically the peakier the distribution, if you take the extreme of 0, 0, 1, then no gradient flows through this because it's completely peaky and basically your gradients saturate to 0. So the peakier it is, the harder it is to learn. So if you increase the size and the scale increases correspondingly, then it becomes harder to learn. So the idea behind this is you just do a simple thing where you scale it by the size of the vector, where the size of k you divide by the size of the square root of k. They just say they do this. I think they probably had a reason why it was square root, maybe corresponding to the variance or something. But this apparently works pretty well and makes the dot product competitive with the NLP. So if you're doing dot product attention, I'd recommend maybe doing this. So I have an example of this in code. I'm going to show this, and the reason why I'm going to show this is because actually implementing this efficiently has a few tricks involved. So the way we do this, or the way we calculate attention, so we have all our boilerplate, we have our train Japanese, train English, etc. And then if we go down to our attention part, we have all our parameters. This is multi-layer perceptron attention, so we have our parameters for the multi-layer perceptron. And then when we're calculating attention, this is our function here. But actually, before we even start calculating attention, at the very beginning of the sentence, there are some parts of attention of the attention calculation that don't change for the entire source sentence. So you're stepping through your source sentence, and you have all your vectors from your source sentence, and these vectors won't change as you step through your output, right? So what you can do is you can concatenate all of these into a big matrix, multiply them by this big parameter matrix, and pre-compute this before you start translating a sentence or something. So that's what this fixed attentional component part is. This is really effective at saving time and memory if you can do that. Then when you calculate attention, basically here we add this attentional component beforehand. Then we multiply the weight matrix for the target with the target output embedding. We multiply this by the weight vector 2, like I showed in the slide, and then we take the softmax. And then based on the output, we take the source vectors and multiply these by the attention weights. Multiply these by the attention weights to get the kind of combined vector. So the important thing here, I guess, that you should know if you're implementing this is you don't need any for loops to do this. If you're writing a for loop, you're doing it the wrong way. So if you're implementing attention, which probably half the people in the class will want to do in your final project, just remember that if it's going slow or something, you can go back and look at this code to find kind of the canonical way of doing it. So yes. Are there any questions about that? No. Okay. So this is kind of review and implementation details and stuff like that. So now I'd like to talk a little bit more about stuff that was not in the reading, including how people use these in NLP tasks, and also kind of new developments in this and better versions of attention. So the first thing, so what do we attend to? Like in NLP, where has this been used? The first thing is the input sentence, obviously. So like the previous explanation and like the explanation in the reading, you can attend to the sentence to get representations that you use in each step of decoding. But as I kind of alluded to in the reading, it's It's also very useful to take a look at the attention weights themselves and use them to bias the model in particular ways. So the most common one is basically a copy-based, a kind of copy-based mechanism. So if you want to output words as is in the source sentence into the target sentence, then you can look at where your attention is pointing to, and then you have a choice between one of two models. You can either generate something directly from your vocabulary, or you can generate something by copying from the original. So this is super, super important for, or it's kind of, it kind of works for machine translation. It's super important for other tasks. Does anyone have an idea of what those might be? Text generation from structured data, that's, yeah, that's one good example. Actually, that's not one of the two I was thinking of. Yeah, summarization is one because you want to keep most of the words. What, I heard a couple others.
Query generation from natural language description, like SQL query.
SQL query generation, yeah, that's another good one. Yeah.
Semantic parsing.
Semantic parsing. Yeah, as long as the stuff in your semantic representation matches English. Yeah. Actually, there's one popular task that nobody has said yet. Yeah. Yes, dialogue. So dialogue, it's very common to repeat things from the previous utterance as well. So like, how are you doing today? Today I'm doing pretty well. Although that's actually not very good dialogue. Yeah, do you like tennis? No, I hate tennis. So you would repeat tennis, for example. So you can also kind of expand this to away from just copying. This is one of my papers, but it's actually pretty effective. And basically the idea is you have a dictionary that allows you to translate words from the source to the target. So instead of just copying, you can also choose to basically pick something from the dictionary, and you use this to bias your models. So this is two examples of a good way to use attention to basically make your models do things better. One expansion of this kind of like copy-based attention mechanism is to condition on previously generated things. So one nice example of this is in language modeling, attending to previously generated words. So one of the features of language is that it's very bursty. Once you start talking about something, you tend to continue to talk about it for a while, because you tend to do topics. Tennis is a good example. You start talking about tennis, and you're going to say racket and tennis a whole bunch of times. So this is an example where basically after you generate a word, now you can do attention to the previously generated words and generate directly from that. In translation, you can also choose to attend to either the input or the previous output. So this is earn sequence files. So there's one really big disadvantage of this method. For example, in speech recognition, it can be kind of dangerous to implement something like this, even though it shows your language modeling results get much better. Does anyone have an idea what that might be? Yeah, exactly. So compounding errors. So the moment you get a mistake in your speech recognition results, you'll continue to make the same mistake over and over again. So it's like me when I go to Starbucks, I say Graham is my name, and everybody thinks it's Grant or Gary or something else. So then it goes all the way down the line, and I get my coffee for Grant. And so you'll get the same thing in your speech recognition as well. Yeah.
Is there some cell which tries to learn whether or not to copy?
Yeah, it's part of the architecture. Actually, you can see down here it has a copy probability, and the copy probability is calculated as part of the network. So they have thought about that. Okay. Another thing is you can attend to things in various modalities, so it's not just text. Actually, kind of the first stuff of for attention was from image captioning. So there's a lot of work on image captioning with attention. You can also do speech. So if you're interested in speech, you have these waveforms that don't directly correspond to specific words, but still you can see if you train an attentional speech recognition model, it can output one character at a time, and each time it outputs a character, you can see it's focusing on a certain part of the speech waveform. And you run the speech waveform through an encoder, of course, so it learns features of the speech and that does this. Any questions? No? Yeah.
So, when people use attention to try to explain deep networks, how much of it is actually explaining and how much of it is you're looking at something that you expect to see?
Oh, that's a very philosophical question. No, it's a really good question. Yeah. I'm actually going to talk about this a little bit in the next class. And basically, it's very easy to cherry pick examples. You can come up with examples that match any hypothesis very easily if you look through 1,000 examples in your corpus, right? So what I recommend doing is if you have a specific hypothesis about the way something should work, you should try to come up with some way to calculate it quantitatively and then calculate that over the entire corpus and see if it's a statistically significant effect or something like that. It's best if you can do that, but in reality, it's not super common. But that's probably what you should strive for. And maybe does that help answer this? So, I think, though, on the other hand, looking at attention matrices tends to be pretty informative. So especially if you look through your entire corpus and you can see that in general it tends to be pretty good, then that...
A lot of image captioning tasks,
yeah.
you end up seeing that for the initial part of the sequence, the model has no idea what is happening. It's attending to some random part of the image,
Yeah.
but then suddenly being reiterating at it.
Yeah, it's really common in text also. So yeah, I'll talk about that a little bit later. Yeah.
Is it mostly used on the decoder side of things, or is it used
Um,
in encoders better also somehow?
So is attention used mainly on the decoder side of things? So attention is mainly used kind of as an interface between the encoder and the decoder. So you have your decoder state, and then you have all your source things, and then based on this, you decide which part of the source sentence to focus on based on your current decoder state. That being said, I will talk a little bit later about self-attention, which is basically to make your encoder better as well. Anything else? Okay, I'll continue. So another thing that is interesting, perhaps, is hierarchical attention. So the idea of hierarchical attention is basically you have attention over multiple levels. This was used for document classification, where basically you have a big document that has multiple sentences in it. In each sentence, you do attention over all the words in the sentence, and then you do attention over all the sentences in the document. So this is it's useful for kind of longer sequences where you want to attend to things in appropriate manner. Another thing that people have done is attend to multiple sources. So one example is attending to multiple sentences in 2 different languages. So if our target is English, and we have 2 translated sentences in French and German, we can simultaneously attend to both of these sentences and use this to generate an output. And the intuitive reason for this is maybe some words in German are better corresponding to words in English. Some words in French are better corresponding, so then we can pick and choose between them. There's kind of a downside to this method. Does anyone have an idea?
The
basically parallel version.
Yeah, exactly. You need bigger or more parallel corpora. So you also need this at test time, right? It's not just training time. You need French and you need German at test time. Fortunately, these cases are much more common than you would expect. So for example, TED Talks. TED Talks are translated into 20 languages already, and then you want to translate them into a new language. So you actually have these 20 parallel corpora. You have them for the UN, you have them for the European Parliament, et cetera. So this is not, an unreasonable, not unreasonable in some situations, but it has to be that kind of situation. There's a comparison of multiple strategies. So do you want to do this by just concatenating the sequences together and attending to all of them as one big sequence? Do you want to do it in a hierarchical fashion, et cetera? So that's good if you're interested in this.
So do I need different attentions if I want to decode into like different languages?
Do you need different attention if you want to encode in different languages? I think the answer is we don't really know yet. So there's been some very nice papers that basically train big multilingual models that work on all languages at the same time. But they also tend to do a little bit worse when you're translating into a whole bunch of languages. So it might be the case that we need to be smarter than that. So I think basically there's no, the research doesn't give one answer to that question. Yeah.
So in the case of particle sources, you mentioned hierarchical. So would you attend on a source first and then a word within the source, or what would the hierarchy actually?
I think usually those two decisions are kind of made into, or wait, let's see. No, usually you attend to the words in the source first and get the sentence representation, then decide which sentence representation to attend to. Okay. You can also do other things like attend to a sentence and an image. So this, in this case, you're given an image and a thing to translate. So for example, if you think about C3PO or something like this, you have a robot that's, that you're going to be asking to translate. It can look at its context in the world, and based on this, it can do disambiguation. And there was actually a task on this, on multimodal translation for the workshop on machine translation, which is a pretty common, which is a pretty well-known workshop. And they created the data. They created the data by basically having multilingual speakers translate while looking at the image or something. But in the end, it turned out that this wasn't really super useful. And in last year's challenge, we created a submission to this, and we tried to use multimodal information and nothing worked. So eventually we just submitted our system without multimodal information, and we accidentally won the challenge. So, I think you can create better data sets for this, and if we have a better data set, then we could probably do more interesting things, I guess. So this is something that's really, the next thing is something that's really popular nowadays because it's been proven to do really well. So the idea is self-attention, and the idea of self-attention is basically that you have two things that are the same. They're the same sentence, and you calculate attention based on this. So remember I was talking before about the query vectors and the key vectors and the value vectors. So in this case, basically our query and key vectors and our, like all of these are very highly related or the same. Like they correspond to the same words. And so as a result, for each word, so if the top one is the query vector and the ones on the left are the key vectors and value vectors, then basically we calculate attention over each word, and we take the representation of the word to be the weighted sum of all of these. So then we'll do something like this. So it's very common to, or well, I guess the most popular methods for this basically take your hidden state H, and you have a weight vector, weight matrix for your query, a weight matrix for your key, and a weight matrix for your values. So basically the input to all of these is the same, but the matrix you use to kind of transform them is different.
So when you do self-attention, what you get, so on one layer you have this is an example.
Yep.
What you get at the third position after doing self-attention,
Uh-huh.
no longer representing the word and.
Not necessarily representing the word and, yes. In reality, it usually does, but it doesn't necessarily. There's no restriction that it has to. But the reason why it does normally, represent and is twofold. Actually, I forgot a kind of important thing actually. So the reason why it does is twofold. One is just because the input is and, the output is and, so they tend to correspond to each other more. If we didn't have these weight matrices, of course they would correspond to each other more because it'd be the same thing. But even with these weight matrices, they tend to learn to maintain the ordering. The second thing that I forgot that's actually really, really important for these models is these models are often used in conjunction with something called the positional encoding. So the positional encoding is basically a thing that you concatenate onto here, which is basically a function of not the input word itself, but the position that it's in. So the positional encoding for the first word in the sentence would be basically P1, P2, P3, P4. And these top vectors here, like H1, H2, H3, H4, these will vary for each sentence. So if it's like this is an example, this will be the embedding for this is an example. But the positional encodings are the embedding for the first word in the sentence, the second word in the sentence, third word in the sentence, fourth word in the sentence. So these are just based on the position, yeah.
So can a similar method be used for like determining polysemy? For example, if you have three sentences, Joe hits a home run, Joe has 13 hits on his Facebook account, and Joe is hitting a dog. So if you kind of like attend to sentences with different contexts like this, and the hit sort of matches the specific polysemy context with respect to a certain hit, could you like sort of update the word embeddings for hit in general so that it's always correct?
That sounds like a good class project. I don't know. I don't think. So these methods basically implicitly capture polysemy. Because if there was no polysemy, you wouldn't need this self-attention. Like if there was no, or sorry, no, that's an exaggeration. But if there was no context sensitiveness to word meaning, then you wouldn't need self-attention because you could just use word embeddings and you'd be fine. One of the things this can capture is that your self-attentional embeddings will change, for different contexts. And one of the things that can capture is polysemy. So if you trained a big self-attentional model and then were able to use that to, do word sense disambiguation, that would be very interesting, I think. But I don't think anyone has.
So just by defining these position vectors,
Yeah.
are you restricting the length of your sentence? That's possible.
So yeah, that's another good question. So by defining these positional vectors, depending on how you define them, you are restricting the length of your sentence. So one way you can define them is just say we're going to learn these. And if you're just going to learn them, then yes, if you have any test data that's outside of the size of your training data, you won't have learned positional vectors. You might have random ones, for example. On the other hand, in the paper, in the Attention is All You Need paper that I'm going to introduce in a little bit, they have this really strange way of defining positional embeddings based on like sine and cosine and multiplication of the sines and cosines and stuff. I don't have the formulas with me and I don't remember them offhand. But the advantage of using this kind of really, if you read it, it's like, how did people come up with this originally? But one of the advantages of that is you can calculate that deterministically for any length sentence. So if you're using something like that, then you could probably still get away with it. Yeah.
So this theory means that a word, if it occurs in a different position, it will have a different embedding. Like you will have multiple embeddings for.
So this part will be different. Yes. The bottom part will be different. If it's in a different position, the top part will be the same.
Does that lead to a lot of sparsity in the embedding?
So would that lead to sparsity in the embedding space? The good thing about embedding spaces is they're dense embedding spaces. So all of the, this positional embedding, if it's size 64, you can share parameters between neighboring embeddings, et cetera. And let's say these positional embeddings aren't useful at all. Let's say they're just contributing noise. Your model can always learn to ignore them. So I think in practice that's not a problem. Okay, so I will move on. There's also been a bunch of improvements to attention. So one thing that's super important and super useful is coverage. So the idea of coverage is that neural models, for especially sequence models, tend to drop or repeat content. So an example of this is, I wish I had an example on here because they're so funny, but it's like my foundation went to the foundation for foundation or something like that. And they just, it found this kind of rare word in the source that it knows it needs to translate, but then it forgets that it doesn't need to translate it 5 times and only once. So one way to help with this is by modeling how many times words have been covered. And there's a number of ways you can do this. So basically what you do is you look at the sum of the number of times a word has been covered. So an example of this here would be, here the sum for this is probably about 3 because it's appending to this word 3 times. The sum here would be 2. So one way to fix this is to basically add a value to your loss function that says this value should be approximately 1 for all of the words in my sentence. So what you're saying is all of the words in the source sentence should be covered about once. Of course, it's a soft constraint, so it can still violate the constraint, but you provide this as an additional term for the loss function. Another way you can do this is to add embeddings indicating coverage. So if you have things that are covered 1 time, then you have an embedding that approximates that. So this is adding a constraint to the loss of your model. This is adding information to your model with the hope that your model will learn to use that well. Another thing that people have done is say that based on your previous attention, you should be able to predict your next attention. So the idea here is that what you do is you basically incorporate information from your last attention vector when you predict the next attention vector. So the idea would be maybe when you predict the next one, you want to step through the sentence word by word. So if your previous attention vector was focusing on this word, then you'll want to focus on the next word most of the time. Another thing that people have done, these are actually all from the same paper. There's one paper that proposes a bunch of different nice ways, is basically that these should be in both similar in both directions. So they should match going from English to Estonian and Estonian to English. And this can be effective as well. Another thing that people have tried is supervised training of attention. So the idea is you can get gold standard alignments. For example, let's say we had somebody annotate a whole bunch of alignments. Manual alignments, or we could also pre-train them with a strong alignment model. Another thing that I forgot here is if you're using something like a copy mechanism, then you know the words that should be copied, you should probably be focusing on that particular word. So there's a number of ways you can incorporate this supervision. And basically what you do is you try to train the model to match these strong alignments. So the idea would be that you have a loss function where if your attention matches the alignments that you know are correct, you have no loss, but if it doesn't match and does something else, you get a loss. So one important thing to remember though is that actually attention is doesn't always correspond to alignment. So one common failure mode of attention is that it actually focuses on the next word over every time. So here the blue boxes are the correct words, while the green boxes are the words that the model actually focused on. And it's pretty, incredible in its ability to get it one off every single time. So the reason why this happens, anyone have an idea why this happens? Or why this can happen and you can still get good accuracy? Sure.
One word is represented by multiple words in
One word is represented by multiple words. That's actually not the reason for this specific one here. Yeah.
It's hard to initialize the attention and then the error gets repeated by the Markov assumption.
It's hard to initialize the attention and then the error gets repeated. That might play a part in it, but that's not the major reason yet.
Because you're using hidden representation, so it actually encodes. Like if you use the second hidden thing, it's encoding first and second.
Yeah, so the answer is basically we have an encoder. We have like a bidirectional LSTM as our encoder. So actually any of the vectors in here, if we have a bidirectional LSTM, have seen all of the other vectors in the sentence. So because of that, the vector for example, Obama has seen all of the other words in the sentence. It's seen Obama through its backward encoder, I guess. So you can actually still do something like this and get this wrong. And you don't normally see this in well-trained models, but in poorly trained models, this phenomenon happens all the time. Another thing that is very common to see is if you have poorly trained models, or if you have a really difficult task like dialogue, it just won't use attention at all. It will, randomly pick the first vector every single time, or randomly pick the last vector every single time. So don't expect to get really good alignments out of this all the time. And this kind of, yeah. Yeah.
But the fact that it has seen all the words, how does that explain one of them?
It's just learned to look at only the forward encoder, or only the backward encoder when it decides to do attention.
It could have been one off in either direction.
In either direction.
But here it's always forward.
Yep. Neural models learn to do strange things. So you can't always explain what they're thinking. Yeah. Go
You see
ahead.
that behavior even in encoders that aren't bidirectional.
Oh, I've never actually tried that in encoders that are not bidirectional. I'm pretty sure you would not see this behavior if you didn't have an encoder at all and you just used word embeddings. So, okay. So there's also a bunch of other types of attention that people use for various things. Yeah, sorry if I'm, rattling off a whole bunch of things. The reason why I do this is because I think a lot of people will want to use attention. And a lot of people will want to use it in different ways. So hopefully at least one of these, says, oh, this might be useful for my problems. Another one is hard attention. So one of the interesting things about, so hard attention is in contrast to soft attention, where you need to make a 0-1 decision to focus on particular words. One thing is this is really hard to train. It requires methods such as reinforcement learning or other things because you can't differentiate between, through hard decisions. I'll be talking about how to do this later, so we do have methods to do this, but they're harder to use. One of the interesting papers in NLP that has used this hard attention is a paper that basically is a text classifier, and this text classifier has hard attention on particular words, and then tries to predict the like features of the output. So one example here is it's a beer review, and you're trying to predict that the beer review look is 5 stars, and this method is able to pick out a very pleasant ruby red amber color. And these red ones are the ones that it chose to focus on, and the black ones are the ones it didn't choose to focus on. One kind of, not necessarily complaint, but one kind of thing that I had about this paper was you probably could do this with soft attention as well. It wouldn't be as crisp, but if you just looked at the places with high attention values, you probably could. But there's also some other things in here, like a continuousness constraint. So they try to get continuous passages. Yeah.
Is this the case with all the whole of the corpus, or is this just?
Is this a cherry-picked example? That's a good question. I haven't run this model myself, so I don't know. But they do have quantitative results that show that it's getting more contiguous things, etc. So I think they do have at least some evidence that it's consistent. Okay. Another thing that might be useful if you're interested in speech or transliteration or some other similar tasks is monotonic attention. So yeah, speech, let's say incremental translation, morphological inflection, or summarization. In these cases, it's very common that you won't actually want to do any reordering, and you'll just want to step through the sentence one by one. One way to do this is through monotonic attention. So monotonic attention basically steps through the sentence in order and will not jump out of order. In many of the examples of this, they combine this with hard attention. So you have to make hard decisions about when to jump forward. But this might also be something interesting if you're interested in these tasks. So convolutional attention. The idea behind this is basically you might want to say, I want to attend to the word after Mr. So let's say the word after Mr. Let's say you want to answer somebody's name. Then having a word be after Mr. is a very kind of indicative feature of whether you should be paying attention to that word or not. You can kind of get this through your bidirectional encoder if you want to express that. You can already kind of get this in your model, but the idea behind this convolutional attention is basically you might want to express that directly in your attention mechanism, and so you look at the surrounding words by using a convolution and then use that to decide where to attend. And then the final one, this is the final big, final methodological improvement. I really like this. The idea behind multi-headed attention is basically, in all our previous models, you had a single attention vector that was telling you where in the sentence to focus on. But in reality, for different aspects of the problem, you might want to focus on different parts of the sentence. So a very direct example of this is a method that has different heads for copy versus regular attention. So the copy, as you remember, copies words directly. So you'll basically want this copy attention to focus very precisely on a particular word that you think you should be copying now. On the other hand, the regular attention kind of summarizes the information that you need to make your next decision. So you might have different attention heads for your summary versus your copy. And here the yellow one is this kind of like summary regular attention, and the purple one is the copy one. So you just learned this attention separately. This was kind of generalized to do attention over different, have multiple heads of attention that don't have any particular semantics. So the top one, sorry, go ahead. Yeah.
So is it like the weight matrices are initialized differently for each of the different attention, or
Are the weight matrices initialized differently for each of the attention ones? Yeah, so you calculate an attention score separately for each of these 2 or each of these 8. And yes, basically that amounts to random initialization. For the first example here, the semantics of each head is very clearly defined. One is for copying, one is for summarizing your context. Here, the semantics is not defined a priori. You just randomly initialize them differently, and you hope that you get different things. So it's like everything else in neural networks. You know, we randomly initialize the weights and hope they learn something that makes sense. Yeah.
These different attentions, do you just concatenate them, or you have another attention over that? Because ultimately you still need a fixed size vector.
Yep, so basically what you do is you have, for this particular one, you have attention separately for each kind of portion of the value vector. So you split the value vector into 8, and then you combine each of those portions differently according to each of these. So one of the really interesting things about this is in self-attention, one of the things that it can supposedly do is like word sense disambiguation, for example. So if we have something like making, here, this word making, it's kind of small, but it says making. And then over here in the other part of the sentence, we have more difficult. So making has a lot of different senses, right? You know, it can mean make bread, it can mean make more difficult. And the translation will probably vary based on these. So you can see that it's decided to focus on more difficult for some of its attention heads, and then it's decided to focus on making for other ones of its attention heads. So some of these heads are, you know, like what can I use to disambiguate? Some of them are what can I, you know, how do we keep the original information about the word itself? So I indeed made a mistake and didn't have my most recent slides. Recently, as of like a week ago or something like that, there was also a paper that did multi-headed attention for basically all of the nodes in the hidden vector. So you have one attention value for each of the hidden nodes. Yeah, I can send a reference to that if anybody's interested.
So each dimension, so if it's 128 dimensions, each dimension gets a different weight.
Yes, a different attention, you know, vector. So that's kind of, you can scale all the way from 1, which is normal attention, to that, which is, you know, crazy 2D attention, or 8, which is kind of like halfway in the middle. So the interesting case study is attention is all you need. This is a very popular paper. It came out like 6 months ago, and it already has 100 citations. But the reason why is basically, it gave really, really good results on machine translation, and it's way faster to train than anything else we have. So just going back to self-attention a little bit, I forgot to mention one really important thing about self-attention. And basically, self-attention is an encoder. So like other encoders, you take a sentence, you take all of its vectors. If it's length 4, you get 4 new vectors, which are basically encode the context. So self-attention is also a type of encoder. You encode the context and you get new vectors for each of the words in the output. If you compare this to a bidirectional LSTM, one of the problems with bidirectional LSTMs is that you have to step through the entire sentence. So you have to have basically a for loop over your sentence. And this for loop can be pretty slow, especially if you're calculating on GPUs or something like that. I mentioned convolution is one way to fix this problem, but convolution, the problem with convolution is it only considers local context. It only considers maybe the surrounding 5 words or something. In contrast, self-attention, it's even faster than convolution because you're basically doing a matrix multiply. And it can consider context from all across the entire sentence. So it kind of has a couple advantages that make it very attractive. So it's fast and effective. So this paper, attention is all you need. The main idea behind it is it is self-attention as an encoder, and then you also use attention in the decoder part. So this is kind of a plate diagram of their model, where you take the input embedding, you take the output embedding, you take a positional encoding. So that's what I mentioned here. You encode the position of all of the things. Then you have n layers of multi-headed attention, and then a feed-forward transformation. So this is basically like a multi-headed self-attention, and then you're transforming it into a different space to kind of get a nonlinearity involved in your model. It also has other things like residual connections and normalization to make sure that everything's in kind of a, to prevent the gradient from disappearing as you go through all these layers, and also kind of make sure everything's in a good space that's consistent. So let me. It incorporates a whole bunch of tricks like self-attention, multi-headed attention, normalized dot product attention, positional encoding. So it's kind of like all of the things that I talked about separately before. It also has a whole bunch of training tricks, including layer normalization, which is basically a method to make sure that everything in the layer stays in a reasonable space by normalizing for its variance and mean. It has a specialized training schedule, which adjusts the default learning rate of the Atom optimizer to do some crazy things like doing a slow start and gradually ramping up the learning rate and then dropping it off. It has something called label smoothing, which inserts some uncertainty in the training process. And it also has masking for efficient training. So basically, if you have not read this paper already, what you should know about this paper is, number one, the results are really good. It's really fast. They have a bunch of improvements. Some of them are ones they proposed. Some of them are from previous work. For attention, they have a bunch of improvements for training. Some of them are previously proposed. Some of them are previous work. So the core idea of using self-attention for everything in a sequence-to-sequence model is very interesting. But they had to put in a lot of work to make it work well. But they did put in that work, and they open sourced their code. So now you can go back and benefit from this. And this actually is a pretty stable recipe for translation now. So just to explain a little bit how it works, one of the reasons why this is so good is you can do training for any length of sentence without writing a for loop, basically. So, or without writing a for loop in your kind of neural network code. So what you do is you set up all of the embeddings for all of the words in the source and target sentences, and you just concatenate them all together into one big matrix. Then what you do is you calculate attention basically n times, where n is the number of words in the target. But every time you do it, you make sure that you can only focus on the words that before the word that you're currently trying to generate. So the first row of this, you're trying to generate the word I. And when you do so, you can only look at the words before the word I. When you need to generate the word hate, then you can only look at the words before the word hate, etc., all the way to the end of the sentence. So the reason why you want to do this is because if you remember, when we calculate the probability of something of the target given the source, we need to make sure that we're always calculating like this, where we only consider the previous words. And this masking that they're doing here is the way to ensure that you're considering only the previous words and you're not considering the other words in the previous. So after you do this, basically the whole model looks like this. You implement each of these layers and you implement all the tricks and it kind of works. Or you download the code for this and run it and it kind of works. So. But yeah, so that's all for attention. I think this paper is pretty exciting. It was one of my favorite papers of last year, my favorite paper of last year. So I suggest taking a look at it, even if the small details are all pretty terse. So I think it's worth reading. Any questions? Final questions? Okay. If not, I will finish up. Thank you.